Hey guys, and welcome to the first of many online video lectures for AP Chemistry. So we're going to jump right into empirical formulas. So I'm going to share my screen with you. This should be review for you from Honors Chem or from General Chemistry, but we'll take our time and go through it. If you have questions, as always, please let me know. So first thing we're going to talk about is how we find empirical formulas. So the term empirical formula means coming from laboratory data. So we'll be given empirical data in several different ways. We might be given it as percentages, mass percentages of the elements. We might be given masses of the elements, or we might be given empirical data in terms of amounts of different compounds that are created in the analysis process. So we'll start with mass percents or grams. If we're given mass percent, the first thing we're going to do is we're going to assume that we have 100 grams of the sample. By assuming that we have 100 grams of the sample, we can just change that percent sign to grams. Then we're going to use the molar mass of each element to determine the moles of each element. Now, empirical formulas are the lowest whole number ratio of the moles of each element in the compound to each other. So in order to get that lowest whole number ratio, we're going to divide by the smallest number that we just calculated in the last step. And that will give us that ratio, and that'll allow us to find empirical formula. So let's jump into an example. So from percent composition, so if we are to talk about para-aminobenzoic acid, or PABA, it's made up of carbon, hydrogen, nitrogen, and oxygen in these percentages. We want to find the empirical formula. So the first thing that we're going to do is we are going to assume that we have 100 grams. So we're going to convert all of those percentages into grams. So you notice that I now have that we have 61.31 grams of carbon, 5.14 grams of hydrogen, 10.21 grams of nitrogen, and 23.33 grams of oxygen. Each one of those we are going to divide by the molar mass of that substance. So for carbon, we're going to divide by 12.01, for hydrogen 1.01, for nitrogen 14.01, and for oxygen 16. When we do that process, you'll see that we come out with 5.105 moles of carbon, 5.09 moles of hydrogen, 0.7288 moles of nitrogen, and 1.456 moles of oxygen. Now, we cannot possibly write an empirical formula like this. Empirical formulas are lowest whole number ratios. These are far from being whole numbers. In order to get to whole numbers, we're going to divide by the smallest number there. So we see that 0.7288. We're going to divide each of these numbers by 7.288. And what that's going to give us is approximately 7 for carbon, approximately 7 for hydrogen, 1 for nitrogen, and approximately 2 for oxygen. If those numbers, you notice that I said approximately, if those numbers are within a tenth, you can round and you can assume that that is the whole number. If the number is off by more than a tenth, then we'll need to multiply by an integer in order to get whole numbers. And if we have to multiply by an integer, we're going to multiply all of them by that integer. So our ratio is 7 to 7 to 1 to 2. So we're going to put those numbers in as the subscripts for our empirical formula, and we wind up with C7H7NO2. And this is what that compound looks like in what we call the space filling model. Okay, let's look at a different example. One more. So this is ethylene glycol. This is the substance used in antifreeze. It's composed of carbon, hydrogen, and oxygen. This time we're going to not only determine empirical formula, but also molecular formula. So I'm going to stop this share for a minute, and we're going to jump into our into a different document. All right, so we're going to have, that was the BA. So we have 38.7% carbon, so 38.7% carbon. We have 9.7% hydrogen, and we have 51.6% oxygen. Get rid of nitrogen entirely here. Okay, so our first step always is going to be to divide by the molar, to change these into grams. Assume that we have 100 grams and change these into grams. So that becomes grams, this becomes grams, and this becomes grams. Now we're going to divide by those molar masses. So for carbon, we're going to divide by 12.01. For hydrogen, we're going to divide by 1.01. And for oxygen, we're going to divide by 16.00. And when we do that math, and I'm going to give you guys a minute to figure this out, we get 3.22 here. We get 9.60 here. And we get 3.23 here. So right now we're showing that we have 3.22 moles of carbon, 9.60 moles of hydrogen, and 3.23 moles of oxygen. So once again, those are not whole numbers. We're going to divide by the smallest one in order to get a nice clean ratio. So we're going to divide all of them by 3.22. And so for the carbon, we're going to get that that's 1. For the hydrogen, we're going to get 3. And for oxygen, we're going to get 1. So our empirical formula, our ratio is 1 carbon to 3 hydrogens to 1 oxygen. So we're going to write that as CH3O. Okay. But then the question moved on and asked us to determine the molecular formula. And in order for us to be able to determine molecular formula, we need to know molar mass. So it gave us a molar mass of 62.1 grams per mole. Now, if we were to determine the mass of this, the CH3O, we have 12.01 plus 3 times 1.01, whoops, times 1.01 plus 16.00. And we get a molar mass of 31.04. What that tells us is that if we take this 62.1 grams per mole and we divide it by the mass that we found for the empirical formula, at 31.04, we get 2. That means that there are 2 empirical formulas in the molecular formula. So we're going to multiply each of the subscripts by 2. And we get C2H6O2. And that's how we move from empirical formula to molecular formula. All right, we're going to go back to our PowerPoint here and talk about the next step. All right, if we have to calculate from empirical data, so it's nice and easy and clean when we're just given masses of each individual element or percentages of each individual element. However, we have to be able to think one step farther. So here's our next example. So we've created a compound. We know that it contains only carbon, hydrogen, and nitrogen. We have a small sample of the compound, 0.1156 grams, and we burn it in the presence of oxygen. And we collect carbon dioxide and water. And it asks us to determine what is the empirical formula of the compound. So let's think through this process. We know that our compound is made of carbon, hydrogen, and nitrogen. We know that when we burn it, we get carbon dioxide and water. Okay, so, and it's asking us to determine the empirical formula. If it only contains carbon, hydrogen, and nitrogen, that means all the carbon is being captured in this carbon dioxide, and all the hydrogen is being captured in the water. and the nitrogen is burning off and not being collected at all. So how can we use this information to determine an empirical formula? If I know grams of carbon dioxide, I can use stoichiometry to figure out the number of moles of carbon. I can use stoichiometry to figure out the number of moles of hydrogen. But I don't have any information about nitrogen. So I'm going to have to go one step farther, and I'm going to have to figure out how many grams of carbon that means and how many grams of hydrogen that means in order to calculate the grams of nitrogen by difference from our whole sample. So let's walk through that process. Oh, and we have a molecular mass of 31.06 grams per mole. So let's go back to our untitled document here, and let's see. So in this case, we have 0.1638 grams of CO2. Oh, I see. And we have 0.1676 grams of water. Okay, so we want to determine moles of carbon and moles of hydrogen. So in order to do that, we're going to use stoichiometry. We're going to divide by the molar mass of carbon dioxide to find the number of moles of carbon. So we're going to divide by 44.01 because that's the molar mass of carbon. And that's going to give us 0.003721 moles of CO2. We're going to divide this by the molar mass of water, which is 18.015. We're just going to call that 18.02. And that's going to give us 0.009301 moles of water. Okay, we're going to pause here for a second because at this point we can figure out the ratio of carbon to hydrogen, and that is a useful piece of information, but we also need to know how much nitrogen we have. So we are going to work backwards, and we're going to say that 0.003721 moles of CO2. Well, I know that for every 1 mole of CO2, I have 1 mole of carbon. And so I can say that for every 1 mole of carbon, I have 12.01 grams of carbon. And so I have here that is 0.04467 grams of carbon. So this is moles of carbon per mole. Okay, so we know how many grams of carbon we started with. We're going to do the same thing to figure out how many grams of hydrogen we started with. So we have 0.009301 moles of water. And we're going to say that for every 1 mole of water, we actually get 2 moles of hydrogen for every 1 mole of water. And we know that every 1 mole of hydrogen has a mass of 1.01 grams. And so we wind up with a mass of 0.01875 grams of hydrogen. Now I know how much carbon was in my original sample. I know how much hydrogen was in my original sample. I can figure out how much nitrogen was in my original sample. So my original sample had a mass of 0. Might have to go back and look. 1136, I think, minus 0.004, 0.044667 plus 0.01875, and we wind up with a mass of 0.0522 grams of nitrogen. Okay, so now we know, because we determined the mass of carbon that we started with, the mass of hydrogen that we started with, we found the mass of nitrogen that we started with by difference. So we're going to come back up here, and in this space we're going to put 0.0522 grams of nitrogen. And now, just as we did previously in determining empirical formula, because this is just the element, we're going to divide by its mass, and we're going to get that that is 0.003709 moles of nitrogen. Now we know the number of moles of each in our compound. We need to figure out the molar ratio. Anytime we're finding out molar ratio, we're going to divide by the smallest number. So we're going to divide by this 0.003709. I'm going to divide by 0.003709, and one more time. Okay, and in this case, that's going to give me approximately 1. This is going to give me 2.5, and this is going to give me 1. So from that ratio, we have 1 to 2.5 to 1, but we need to recognize that this is moles of water. And for every 1 mole of water, we have 2 moles of hydrogen. So we have 2 moles of hydrogen per mole of water. So this is 5. And so our ratio is 1 to 5 to 1. So we're going to write our empirical formula as CH5N. Okay, a few more steps when we're given pure empirical data. Now let's look at what this looks like in the context of some other applications. So we can use mass percent to tell us about the purity of a substance. We can use mass percent to determine the identity of a contaminant in a substance. So let's talk about how that works. So here's an example. We have 2 pure compounds. We know that they both contain the chlorate ion and that they're both 1-to-1 ratios. Our student measures the mass of each sample and then heats the samples. When that happens, all the oxygen is going to be driven off. The student can then measure the mass of the solid residue from each sample. Which questions can be answered? So let's think about what this process tells us. By heating this and driving it off, by measuring the mass before and measuring the mass after, we know how much oxygen was driven off. If we know how much oxygen was driven off, then we can determine how many moles of each of our compounds that we have. So if we can determine how many moles of each of them that we have based on the oxygen, we can then determine the molar mass of both XCl and ZCl, since we know how many moles there are and we know what the mass is. So we certainly can answer the greater molar mass question. Which has the higher boiling point? I don't think we can answer that because we haven't taken it to a boiling point, nor have we taken it to a melting point. And unless we've measured the volume, and none of that was not given to us in the question, then we can't answer a question about density. But we can answer the molar mass question because from only the oxygen information, we can determine how many moles of each substance we had. Okay, more analytical problems. It says, our 2 ionic compounds each contain only copper and chlorine. Both compounds are powders. This elemental analysis is performed on each powder. So elemental analysis is like what we discussed with the determining the empirical formula. That's where something is heated and until it decomposes and the pieces are collected. So it says, which of the following questions about compounds is most likely to be answered by the results of the analysis? Well, we know copper and we know chlorine. Again, we didn't measure volume, so I don't know how we would know anything about density, but we can determine how much copper was collected, how much chlorine was collected, and from that, we can determine the formula unit of each compound. So moving on. All right, now we have a mixture. We have a mixture of sodium chloride and potassium chloride, but in different proportions. So it asks, which of the following pieces of information could be used to determine which mixture has the higher proportion of potassium chloride? So if we think about our mixtures here, both sodium chloride and potassium chloride are going to be white powders. If we want to determine which mixture has the higher proportion, volume is not going to help us. Their densities are going to be too similar. Mass of chlorine in each mixture. Well, if I know the mass of chlorine in each mixture, then I know that the rest of the mass comes from sodium and from potassium. If most of the mass comes from potassium chloride, then the mass of chlorine is going to be smaller in proportion because that means that we're going to have more potassium, which is a heavier element. Number of isotopes isn't going to help us, and those are both going to be soluble in water. All right, I think this is our last practice problem. So we have this 5-gram sample of magnesium chloride. It might contain some other impurities. How would we know if this sample is pure? Color and density, well, those are both useful identifiers, but there are a lot of things that have similar densities and certainly that have similar colors. If I only know the mass of magnesium, well, can we figure it out? Certainly it's possible. All right, if I only know the number of moles of chlorine in the sample, it's a little bit difficult as well. But if I know the mass of magnesium and the mass of chlorine in the sample, then I can use empirical formulas to determine whether or not this sample is pure. Okay, and tomorrow we will talk about determining hydrates, and we've already talked about determining empirical formula. So that's it for today. I know it's a lot of information, and if you have questions, as always, let me know.